I'm going to start recording now. So just take a few minutes to go over these problems. One thing that will help me is if you feel like you have completed the problem, or if you're stuck, if you could use the yes function in the participant section, and that will let me know whether or not we're looking ready to move on and go over the answers. So when you're stuck or have figured it out, feel free to click the yes button. And once enough people have, we'll move on. We'll give it a couple more minutes and then we'll talk about these answers. Okay, so both of these problems I think are pretty interesting electrophilic aromatic substitution chemistries, as well as some new nucleophilic aromatic substitution chemistry that we talked about just this morning in class. So also, just a reminder to all of you that you really need to watch all of Felix's lectures, and he has now posted a recording of this morning's lecture on B courses that everyone should check out. It covers the last really important reaction for the purposes of the exam, which is the nucleophilic aromatic substitution chemistry, and that will certainly you'll certainly be responsible for that on midterm 2. So make sure you know your SNAR. So when we're approaching this first problem here, I think the very important connection we have to make is the fact that we're cleaving a carbon-nitrogen bond and instead forming a carbon-carbon bond. And so when we think about the cleavage of carbon-nitrogen bonds, and here we see in analyzing this problem, we have to convert the CM bond to a CC bond, we should always be thinking about the Sand-Meyer reaction. Right? We learned the Sand-Meyer reaction is a very powerful tool for transforming carbon-nitrogen bonds into a variety of different functional groups. So here is just a quick review slide from last week on the Sand-Meyer reaction. And we have to recognize and know all the different things that we can turn these carbon-nitrogen bonds into. And so under the conditions of sodium nitrite and an acid, you can form diazonium salts. And these diazonium salts are widely diversifiable. So if we treat with copper chloride, we can make a carbon chloride bond, copper bromide, carbon bromide. Copper cyanide, very importantly, can install a nitrile group, which is a CC bond. Potassium iodide gives us a carbon iodide bond. Hydrogen tetrafluoroborate puts in a fluorine. We can put in oxygen, and we can also just reduce it off. And so all of these transformations are really important, and we should keep them all in mind when approaching these problems. And so the key to this problem was the recognition of the fact that you could use the Sand-Meyer reaction to replace the carbon-nitrogen bond with a carbon-carbon bond. And so very simply, if we treat this compound with sodium nitrite and then copper cyanide, we can install a nitrile. And we know that the nitrile group can be reduced using lithium aluminum hydride to the corresponding amine, and then that amine can be protected as the amide to give our product. Okay, so I think that this problem, you either get it or you don't, and you figure it out based on your knowledge of the Sand-Meyer reaction and the transformations you can do from it. So it's really crucial that you understand all the ways that you can apply that reaction. Any questions on this one?
Sorry, why do you need the AC2O instead of like could you try and use, well, never mind. I was gonna say like an A solution, but that won't work. Is there like a different way to do that, or do you have to use like the
Yeah, so you could
AC2O
use
and DMAP?
acyl chloride. You could also use acetic acid and DCC to do a DCC coupling. But these are pretty robust conditions for the formation of amides. So you can certainly use these, but there are a variety of other ones that we've used in class that are perfectly acceptable as well.
Okay, thank you.
Any other questions? Okay, so the second problem here is perhaps a little trickier, and so when we're thinking about this, we look at the product and we can start thinking about some of the chemistry that we talked about earlier today in the nucleophilic aromatic substitution chemistry. And so you see in this molecule, we have a methoxy group here that is ortho and para to 2 electron withdrawing groups. And when you see this kind of structural motif, you should say to yourself, this could likely come from a nucleophilic aromatic substitution chemistry. And so let's take a second to talk about nucleophilic aromatic substitution chemistry. This is the process by which a leaving group on an aromatic ring, this is normally fluoride or chloride, can be attacked by a nucleophile to generate these resonance stabilized anions known as Meitzenheimer complexes. And here I've drawn the 3 resonance forms available to it. And then after addition, elimination of the X group as our leaving group generates our substituted product. So in this way, we can use a variety of nucleophiles to substitute off halides from our ring, specifically fluorine and chlorine. And so what we also know is when we look at these resonance structures, we see a buildup of negative charge, both ortho and para, to our leaving group. And so with that in mind, we know that electron withdrawing groups, ortho and para, to our leaving group greatly accelerate the rate of nucleophilic aromatic substitution. And so while normal unsubstituted benzenes are not very reactive in SNAR chemistry, once you start putting electron withdrawing groups, ortho or para, to that X group, they greatly increase in reactivity, and it's very useful chemistry. And so when we are in a situation where we have electron withdrawing groups, ortho and para, to what could be a nucleophile group, we should think to ourselves that could come from SNAR chemistry. Right? So it's a very key structure that you should keep an eye out for. Okay, so returning back to the problem, we see that we have a methoxy group, ortho and para, to our nitro and sulfonyl group. And so we can work that back, if we work backwards, to a leaving group there. So we could say fluoride, it could be chloride, whatever we'd like. And so we know that in the forward sense, we can introduce a nucleophile and displace that leaving group. Then we know that a fluoride can be obtained from our amine using the Sand-Meyer reaction, just like before. And so we can work back to an aniline. And then all we need to do is introduce the nitro group through nitration, which should go ortho to our directing amine. And so if we're thinking about building this up in the forward sense, the first reaction would be a nitration. This goes ortho to the amine. The second step would be our Sand-Meyer reaction, where we convert the amine to a diazonium salt and then treat with hydrogen tetrafluoroborate, to install the fluoride. And then simply an SNAR reaction with sodium methoxide can generate the desired product. Okay, so the key recognition here is that we can install this carbon-oxygen bond by turning our carbon-nitrogen bond into an electrophile, like the fluoride here. Any questions on this problem?
Oh, does the acid remove the SO3H group?
In in either of these cases, you mean either in the nitration or in the Sed-Meyer reaction?
Yeah.
I think that would be something that you could control by reaction conditions. Typically, you need dilute aqueous acidic conditions to remove the sulfonyl group. So I think it would be avoidable by concentration control.
Okay.
That's a good question, though. I would say in general, unless you're trying to take off the sulfonyl group, it stays on pretty readily.
Okay.
Similar for the nitro group, would that be messed up under acid?
Say that again.
With the nitro group, I think in the book there's like some condition where they use acid to turn a nitro into an amine.
I think the reaction may be, and maybe you could find the specific section that you're thinking about. But typically, in order to use acid to turn a nitro group into an amine, what you also need is some kind of metal like zinc. So you can use zinc and acid to reduce nitro groups to amines. So just acid itself will not harm a nitro group. Good question. Any other questions? Okay. And so these are two examples, I think, of the ways we can use electrophilic aromatic substitution chemistry as well as nucleophilic aromatic substitution chemistry at the same time. We're going to be doing more synthesis problems later, but the next problem we're going to be tackling is a mechanism one. And so this is the Vilsmeier-Heck reaction, a reaction that we should be getting familiar with as a really powerful way of building carbon-carbon bonds onto electron-rich aromatic rings. And so I'll give you around 10 minutes or so to look through your notes, work on this problem, try and do the problem without your notes first, and then come back and check your notes. And also get or use your chemical intuition as well as your notes to determine at what position on the indole we're going to functionalize. And so we'll give you quite a few minutes for this. Yes, you should assume there's a water workup. Okay, so let's talk about this problem a little bit. I'm going to try a couple things here so on the next slide, I have what my drawn out answer is, but it's like a picture of a piece of paper. I took a picture of it. That doesn't look as cool as drawing it out using PowerPoint and a mouse. So I'm going to try that, and then when it falls apart, because it's pretty hard to draw using a mouse on PowerPoint, I'll just move on to the next slide. I'm gonna try and figure out a way to be able to write on the board better for you all to see, because I do think that is the best way to learn organic chemistry, is to do it while writing and to talk about it while writing. But I don't have a solution for that just yet. We're gonna try PowerPoint. I don't think it's gonna work. I was practicing earlier. I'm not very quick at it. But the reaction here is the Wilsmeyer-Hack reaction. It allows for the addition of essentially what is an aldehyde to electron-rich aromatic rings. And the reaction proceeds. Yeah, so to answer your question in the chat, I have asked many of my friends if they have a pad with a stylus that I can borrow. And I have no takers yet, and now we've entered full quarantine mode. But to continue, the Wilsmeyer-Hack reaction involves generating an activated electrophile and then using our aromatic ring as the nucleophile to attack that electrophile. And so here we have our the reagent DMF, dimethylformamide. Here. This is DMF. It's a very common solvent, and it's quite useful in this case because with the use of an activating reagent like phosphorus trichloride, I forget what its actual name is, POCl3, we can activate this toward a nucleophilic attack. And so the way this activation works is we have DMF here, and our phosphorus species is electrophilic phosphorus and loves to make oxygen phosphorus bonds. And so from the lone pair of DMF nitrogen, we can push to form a carbon oxygen bond between the carbon, between oxygen and phosphorus, and the electrons are taken up into oxygen. This reaction is quite favored due to the fact that, once again, we are forming a oxygen-phosphorus bond, which are very strong. So now we have this activated species, in which negative charge resides on this oxygen. And positive charge on nitrogen. And now the species can collapse to eject the chloride. This is once again favored by the fact we're forming phosphorus oxygen bond, cleaving phosphorus chloride bond. The drawing is going surprisingly well. I hope you're having fun. So now that we've arrived at this species, the carbon shown here is quite electrophilic, and so the chloride that we just ejected can come back and act as a nucleophile to form a tetrahedral intermediate, and give some equilibrium arrows for forming tetrahedral intermediates if we want. Okay, so now we have our tetrahedral intermediate, and it can collapse like so. To give our crucial activated electrophile. Okay, so this activated electrophile here, it's called the Vilsmeier reagent. We'll recognize that this is quite a bit more electrophilic than the parent compound DMF. And that's not only because it's positively charged, but because the carbon here is now bound to a chloride as well, which is quite electron withdrawing. And so this is like the an activated version of an acyl chloride and is quite electrophilic. And so this whole first activation step is just to generate our Vilsmeier reagent, which is the electrophile in the upcoming electrophilic aromatic substitution chemistry. So now that we have an activated electrophile, we can react that with our nucleophile of choice. In this case, this is the indole. And so if we look at our notes, we'll see that indoles are nucleophilic at C3. And so the way we count indoles is 1, 2, 3, 4, 5, 6, 7. We skip these positions. And so the indole is nucleophilic at C3. We can talk about why in a little bit. And so it can attack our electrophile at C3 from the C3 position. This is an N, not a W. I apologize for that. And this is, of course, a double bond. Now, upon loss of this proton and restoration of aromaticity, we can regenerate the indole, classic electrophilic aromatic substitution chemistry. And then the lone pair of the nitrogen comes down, kicks out the chloride. Now we have another iminium species. And then upon water workup, this gives us the, ooh, that was bad. C3 formulated product. Okay, so the Vilsmeier-Hock reaction is a classic electrophilic aromatic substitution chemistry problem, right? It's broken up into two phases: activation of electrophile, followed by, and so this part here is the activation of our electrophile. The step is always specific to the electrophile that you're using, and it's kind of the nuance of these mechanisms. But it always starts with the activation of an electrophile. You form your activated electrophile, like here, the Vilsmeier reagent. Then the aromatic ring breaks aromaticity to attack the electrophile. That gives us what is known as our Wieland intermediate. So these are resonance stabilized carbocation or resonance stabilized cations. This is a Wieland intermediate. And then a loss of a hydrogen or of a proton restores aromaticity. And we've completed our electrophilic aromatic substitution. Is there any questions on this problem? Yeah, so there's a good question. Does the reagent have to be an aldehyde, or can the H be any R group? It turns out the H can be many different R groups here. The classic Wildmeyer-Heck reaction uses DMF because DMF was such an available reagent, and so it's historically notable. But it's absolutely true that this H can be many different R's, typically limited to alkyl groups or aryl groups. It can't, for example, be like chloride or bromide or something. So it should be carbon. Another question is, why aren't all of these equilibrium arrows? Many of them, I guess, should be. We can add in some equilibrium arrows here. A couple of these I would imagine are effectively irreversible. For example, this step where you're forming a carbon-oxygen bond and cleaving carbon chloride or phosphorus chloride bond, I would imagine is effectively irreversible, as is the formation of the Vilsmeyer reagent. The first step in electrophilic aromatic substitution can be irreversible, but the restoration of aromaticity is certainly irreversible. So in general, with the electrophilic aromatic substitution chemistry, we care less about the reversibility of arrows because these processes are, for the most part, effectively irreversible at the end stage. This is different than what we've talked about previously in aldyl chemistry, where all those processes are reversible. Here, the only one that's really reversible is sulfonylation. And so we care a little bit less about those arrows. And so a couple more questions in the chat is, in general, should we reform aromaticity before any step or any other step? I would say in general, yes. That's going to be the fastest reaction because of the huge energetic payoff for that. And someone else asks, how do we know when something is electrophilic enough to react with SEAR? It's hard to know that from first principles. It really is more to do with knowing the reactions available to you, right? So you know that for Friedel-Crafts type chemistry, we're forming, for example, if we were to do a Friedel-Crafts type reaction, when we react acyl chlorides with aluminum trichloride, we end up making acylium ions, which are activated electrophile in that case. And so to get to the question, it's hard to say or hard to know what the if something's an active enough electrophile. But when you start to, and so what you have to just do is know the different chemistry available to you. So you should know what the activated electrophile looks like in a Friedel-Crafts type reaction. You should know what the activated electrophile looks like in the Vilsmeyer-Heck reaction. And it goes for nitration and sulfonylation and bromination. All these activated electrophiles are slightly different, but they're well studied and we've covered them in the class. And so you should have a general sense of who the electrophilic species is in this case. Someone else asked if we wanted to add a carbonyl, could we also do a Friedel-Crafts acylation, and would there be any preference for one? Yeah, so the Friedel-Crafts acylation is a great choice. The only reason you wouldn't want to use it necessarily is, for example, if you had something that maybe is perhaps Lewis acid sensitive. So if you don't want to use aluminum trichloride with your molecule, you could use this. Also, this is very good for adding in aldehydes. Friel-Crafts acylation gives you a wider range of things. Of course, like we just discussed, you could use other amides for this chemistry. But really, the reason for this is we like to have the ability to do the same thing in many different ways. It just allows for a bunch of compatible reactions. I will say a key part of this reaction is that it requires an electron-rich aromatic partner. So the indole, for example, is electron-rich. So we always will need electron-rich aromatic rings in order to do the Vilsmeier-Hack reaction. Another question is, what's the difference between the Buchler-Naparowski reaction and the Vilsmeier-Heck? Mechanistically, they're quite similar, but one is yeah, mechanistically they're quite similar, but they aren't quite the same. One is a ring synthesis and the other is a formylation reaction. They have similar mechanistic steps, but the products they make are quite different. Any other questions on this? I can, as we work on the next problem, I'll bring a picture of the Buchler-Naparowski reaction to make clear what I'm talking about. Okay, I'm glad the writing using the PowerPoint worked okay. You can see this is what I was going to do earlier, which is, I think, less fun. And so here's problem 3. Start working on problem 3, and we'll take a couple of minutes to do that. We'll do probably like 10-15 minutes to work on problem 3. I'm going to take a quick break to get a drink, and then when I come back and get you guys a picture of the Buchler-Naparowski reaction, we'll take a look at this. So feel free to ask questions in the chat in the meantime. I just wanted to make a reminder. I sent out an announcement earlier today with a link to a doodle poll about people's availability for midterm 2, whether they could handle it entirely online or whether they required a hard copy of some sort due to lack of a printer or scanner. So please, if you haven't taken a look at that poll yet, most of you have. If you haven't taken a look at the poll yet, please fill it out. It's going to make me and Felix have a plan on how we're going to handle the students that don't have access to printers or scanners and how we can handle their exams. So knowing who those people are and how many of them are is pretty crucial. So if you could make sure that you fill out that doodle poll, I'd be really appreciative. Okay, let's take a couple more minutes and then we'll talk about these. Okay, first thing I want to talk about, I just want to address a question from earlier about the Bieshler-Naparowski reaction. So hopefully, go ahead and erase all the ink on this slide. I posted here the mechanism of the Bieshler-Naparowski that I copied from the internet. This is a reaction that's a ring synthesis reaction that follows a very similar mechanism to the Vilsmeier-Heck reaction, wherein the amide is once again activated. We make an activated electrophile. In this case, they draw the mechanism slightly different. I would ignore this stuff mostly, and think about this just like the Vilsmeier-Heck reaction, but intramolecular. And it being intramolecular, you make a stable imine at the end. And so our product here is a dihydroisoquinoline. Oftentimes, this reaction is very useful because upon treating with an oxidant, we can take our dihydroisoquinoline and oxidize it to the corresponding isoquinoline, which is a useful electron-poor heterocycle. And so while it is a mechanistically related reaction to the Vilsmeier-Heck, it is slightly different in the product it is forming. Any questions on that? Okay. And so when we are, what kind of oxidant should we use? It's a good question. You can use a variety of oxidants, MTBA, manganese dioxide. What are some ones we use in class? Yeah, so I would say like MTBA. You can also just use, a lot of times, just molecular oxygen will do the job. So just like O2. But in synthesis, you would use maybe something like MCBPA. You could use permanganate. It's a little harsh. Yeah. But for the most part, molecular oxygen will also just do the trick. Yeah. So here are three problems revolving around electrophilic aromatic substitution chemistry and some nucleophilic aromatic substitution chemistry as well. And so we're going to talk about the ways we can approach these synthesis problems. Oops. I think on the worksheet, I copied the ethyl group over, so we can do this problem with this ethyl group there or not. It doesn't. It's pretty much the same. But anyway, when we look at the problem here, we see that we have, relative to this nitro group, we have groups in the ortho and para positions. What that should always tell us is that if we had this nitro group as an ortho-para director, it could have a matched relationship with both those positions. So it would direct those positions. We know, of course, that nitro groups are meta-directors, but we know chemistry to interconvert them between amines and nitro groups. Amines are ortho-para directors, nitro groups are meta-directors, so in this way they're kind of like a molecular switch. And so the key strategy here is going to revolve around using an amine directing group to put in these groups ortho and para, and then converting it to a nitro group. And so I think that's the kind of recognition you have to be able to make when you see, for example, this electron withdrawing group, ortho and para, to the groups we want to put on this molecule. And so if you make that recognition, you can then work this back and say, okay, so this nitro group was an amine-derived directing group, like this amide. And so if we have an amide on the molecule like this, I think it's pretty straightforward using the chemistry we've learned to install both these ethyl groups and the nitro groups. Right, so we can we can work it back. We'll put in the ethyl groups after we put in the nitro groups because we know there's this preference for para substitution. And so we'll put in the nitro group first, then both the ethyl groups. And so we have to just get, and we know that we can get this amide from a nitro group. And the nitro group we can get from just nitrosylating benzene. And so in order to make this amide, we can hydrogenate our nitro group and then protect it as the amide using acetic anhydride and DMAP. Then we can nitrate the para position. Then Friedel-Crafts alkylation reaction on the two ortho positions can install our two ethyl groups. And finally, acidic cleavage of the amide. You could also use basic cleavage of the amide, doesn't really matter, followed by treatment of the resulting aniline with trifluoroperoacetic acid. That looks like and this reagent can convert anilines to nitro groups. And so I'm getting a couple of good questions in the chat, and one good question is this protection step necessary? Do we need to have a protected aniline for our Friedel-Crafts alkylation? And the answer is yes. So if you have a free aniline, if you have the free aniline unprotected, it will react with the Lewis acid, in this case aluminum trichloride, to form this Lewis acid-base adduct, and this makes it unreactive in the Friedel-Crafts alkylation reaction. And so you do need to do a protection step here. And so there's another question, a general question on when do we use DMAP just to make the ester and amide? Yeah, so DMAP is really useful for base catalysis. It's not strictly necessary in this case. I'm just showing what the best possible conditions are, but it helps to accelerate the acetylation process. It's not strictly necessary, but the reaction is oftentimes sluggish if you don't have it. It's very useful for activating not only esters, but also anhydrides toward nucleophilic attack. And so if you want to, attack an ester or attack an anhydride, you can just drop DMAP in. So there's an alternate solution, which is So first nitration, then hydrogenation, then Friedel-Crafts. Yeah. If you first do nitration and then Friedel-Crafts alkylation, how many times would it add? Yeah, and so a couple of questions there. So if you first do nitration, and then try and do Friedel-Crafts alkylation, this is a problem because the aromatic ring is not nucleophilic enough in order to do Friedel-Crafts alkylation. You can potentially get away with it under very forcing conditions, but what I would say in general is that this is not a viable reaction. So you don't want to do nitration first and then try and put in these alkyl groups meta because it's not a because the aromatic ring is too electron deficient. I see another question asking if we can use potassium hydroxide and water to remove the acetyl protecting group. You can. It can be removed under acidic or basic hydrolysis conditions. Any more questions on this? Okay. I'm going to erase the things I've written on the slide, but I think what you should get out of this problem is recognizing the relationships on the aromatic ring, and when you look at those relationships, you can find out which ones have been switched in their directing character. And so here, when we looked at the nitro group and we saw the groups ortho and para to it, we say to ourselves, that could have been an ortho-para director, and it allowed us to solve the problem. If the protecting group was removed with potassium hydroxide and H2O, do we get an amine or a nitro group? We get an amine. A nitro group requires an oxidation step from the amine. It's at a higher oxidation level than the amine. And so you need to use an oxidant like trifluoroperoacetic acid in order to go up in oxidation level. Hydrolysis is a oxidation neutral process. Right, can you also use an sulfonyl blocking group to add the ethyls? Once again, the issue with that is you would have an electron deficient aromatic ring, and electron deficient aromatic rings are poor for doing Friedel-Crafts alkylation. It turns out that in Friedel-Crafts alkylation, the electrophile you're generating is not super electrophilic. It's quite electrophilic, but not electrophilic enough to react with electron poor aromatic rings. And so their poor substrates for doing Friedel-Crafts alkylation are those that have only electron withdrawing groups on the aromatic ring. For example, like we were talking about, the nitrobenzene does not do Friedel-Crafts alkylation readily. Okay. Okay. So as we look at problem 2, we can see that the nitro group and the alkyl ring are ortho or meta to each other. And this is not a well-matched relationship. So this is another case where we could think about this is another case where you need to think about switching the character of one of these groups, because when you have a mismatched relationship, you should recognize that one of those things likely used to be something else. And so in this case, we'll once again think about switching the character of the nitro group. And so if I thought about working this compound back, I want to put in an orthopara directing group, but then I would also recognize the fact that if this nitro group was an orthopara director, it would direct the Friedel-Crafts alkylation to the para position. So what we also need is a reversible para blocker. And so we can do that using sulfonylation chemistry. We can install a sulfonyl group in the para position and allow us to gain selectivity for the alkylation positions that we want. And so once we have a para blocker installed, we can do a Friedel-Crafts alkylation to install that ring. And then that gets further worked back to this amide. And of course, we know how to make the amide from there. Now, if we treat this with fuming sulfuric acid, it will sulfonylate the para position preferentially. Then a Friedel-Crafts alkylation reaction can install the desired ring. Oops, screwed up my animations here a little bit. And then cleavage of the amide under acid hydrolysis conditions, which we could also tune to get rid of the sulfonyl group, because we know that the way to remove sulfonyl groups is using dilute aqueous acidic conditions. And then once again, oxidation of the free amine with trifluoroperoacetic acid can reinstall the nitro group. And so in this way, we can resolve this mismatched relationship we have here. Why does the alkylation add to both the ortho and meta positions? Yeah, okay, so two interesting questions here. Why does the alkylation add to both the ortho and meta positions? So the first position it adds to is ortho. And so we get a substrate that looks like this. And so it turns out that the second step here is controlled by proximity and not necessarily by the electronics of the ring. And so it favors the formation of this CC bond because it's the only one accessible to it. Someone else asked the question of it, can it form, for example, this CC bond? But bridging over benzene rings creates quite strange structures. It's very difficult for the benzene ring to maintain this 120-degree bond angle that's crucial for aromaticity if it has a bridging group over it. And so those structures tend to be very high in energy and unlikely. And so even though it's electronically not preferred, it will form this second CC bond to the meta position. Does that answer both those questions? Okay, and so some more questions. On the exam, what should we do if our list of reagents to answer a question like this one is too long to fit in the box provided? First, try your best, but if it's under the box, we'll still be able to see it, and that'll be okay. So don't worry about it too much. As long as part of your answer is in the box, we'll have our eyes and we'll be able to see it. Someone else asked, can we first do Friedel-Crafts acylation, then nitration, then reduce it to H2, protect it, and put the sulfonic acid and do another Friedel-Crafts alkylation. So do something like Friedel-Crafts acylation, then nitration, then reduce it, protect it, put on sulfonic acid, then do another Friedel-Crafts alkylation, remove it. Yeah, that the step, I don't know if that is it the same step count or not. It seems reasonable. But one thing I'd be worried about is when doing the Friedel-Crafts acylation is the formation of the second carbon-carbon bond. It might not be a problem due to the fact that the carbon-oxygen can sequester the Lewis acid and stop catalysis, but it is a problem to worry about. Wouldn't there be carbocation rearrangements in the Friedel-Crafts? Why is there not a carbocation? Yeah, that's a great question, and I do actually now remember my original answer to this. Yeah, a couple of people have pointed this out. There is, in fact, you would have the possibility of carbocation rearrangements. I'm sorry, I forgot to change my answer here. So let me be clear on that for everybody. That was a. I'm gonna just erase all the stuff on the slide and handle that question because that's a great point. So, as many people pointed out, the problem currently that I forgot to change is that when this substrate undergoes Friedel-Crafts alkylation with primary alkyl chlorides like this, we know that you generate carbocations, and these carbocations can undergo 1,2 hydride shifts. And that would get you to new, more stable carbocations, like this. And so you would see some degree of branching in your product because the aromatic ring would attack the secondary carbocation. The way, of course, classically to avoid doing this rearrangement is to add these groups as is to add instead the acyl chloride. These do not undergo rearrangement. And so you could get to products that look like this. These exist in another tautomeric form, but that's not a huge problem for us at the moment. We could reduce these using Clemenson reduction conditions. So that is a great point, something that I had forgot to account for. And so a better answer here is to use the bisacyl chloride and then reduce it using Clemmensen type reduction conditions. Another question, if we turn the NO2 group into the NH2 group, we turn the NO2 group into an NH2 group. Yeah, to another question, we're always looking for the highest selectivity as possible in our synthesis. So always try and block para positions if need be. Yeah, and another question is the Friedel-Crafts reaction possible despite the deactivating sulfonyl group because of the activating amide, and that's absolutely correct. And so while we did just say it's difficult to do Friedel-Crafts reactions with electron deficient aromatic rings, in this case, our aromatic ring is not electron deficient because while we have an electron withdrawing group, we have also an electron donating group. In fact, you pretty much always listen to the electron donating groups when it comes to activation. Any more questions? Does the Clemmensen reduction cleave the amide protecting group? No, probably not. Amides are less easy to reduce than ketones. It has to be aqueous acid conditions. And so the Clemmensen reaction can be done under not vigorous aqueous acidic conditions. It might remove the protecting group, but wouldn't matter so much. So should we cleave the amide first and then reduce the two ketones? You could. I mean, honestly, at that point, the need, once you've installed the ketones, the need for the protecting group is obviated. So you could remove the amide at any point. So if you wanted to remove it during the Clemmensen reaction, you could as well. The point here is that you could do a Clemmensen reaction with an amide group in place, and it would be fine, despite the fact that there is acid in the Clemmensen reaction. You could probably do it in such a way that it leaves the amide on. It's just an operational thing. Any more questions? Okay. Next problem. So I think the key recognition to make on this problem is that we have this methoxy group, ortho and para, to two electron withdrawing groups. And as we said earlier, this should be a red flag to you for seeing an SNAR reaction problem. And so if I think that this methoxy group was placed on the ring using SNAR, then I can work it back to a halide, like a chloride. And then from that chloride, I can say, okay, well, now we have this aromatic ring. The nitro group here is meta and para to the two groups. The chlorine is meta and ortho to the ketone. And the ketone is ortho and para to the two groups. And so when I consider those three sets of relationships, the only one that's completely matched is the ketone, right? And so since the ketone has something that's ortho and para to it, we would say at one point that ketone was likely an ortho-para director, right? And so by looking at the three sets of relationships, I picked out the fact that this ketone could have been an ortho-para director like the ethyl group. And so the ethyl group is orthopara-directing, and we know that we can reduce ketones to ethyl groups and vice versa. And so this is an easy way for us to switch between the reactivity. And so if that's the case, we can also remove chlorine, and then we can remove the nitro group and get to ethylbenzene, which we know we can make. Okay, so with that in mind, if we thought about going forward, we'd do a nitration reaction, then a chlorination reaction, then a benzylic oxidation, and then finally an SNAR reaction to displace the chloride and install our methoxy group. And so in this way, we've recognized that the two key relationships here. One, this came from SNAR, and two, this could have been an orthopara-director. Once you make those two recognitions, the problem falls into place. Any questions on this? Okay. If there's no problems on that, we're going to go on to problem 4. And so problem 4 is assign the oxidation level. Book has it that the potassium permanganate turns anything into a carboxylic acid. Yeah, this is an area where Felix has kind of differed from the book on the reaction of potassium permanganate. It's very oxidizing, and it can certainly, if you force it, turn this into the carboxylic acid. For the purposes of this class, we'll say that you can use potassium permanganate to do these benzylic oxidations. But you're certainly correct that in many cases, especially in the real world, it can over-oxidize products. And so there's other benzylic oxidation methods available in chemistry, but this is the one that we've learned for the class. And so feel free to use it. If the nitro group had been okay, so someone asked, would you just use Friedel-Crafts to add the ethyl? Yes. Could we have nitrated the benzene first, done a Friedel-Crafts, then reduce the carbonyl to get the so I assume you mean nitrated, then chlorinated, then reduce the nitro group to the amine, then done the Friedel-Crafts, which would work, I think. Did I use a Friedel-Crafts acylation or alkylation in the first step? Both would be okay. It's a little tricky to stop the Friedel-Crafts alkylation after one alkylation. It tends to keep going, but it would be an acceptable answer. So Friedel-Crafts acylation or alkylation would be fine. And one more question. If the nitro group had been an amine, how would we have added only one chloride? I don't quite understand that question. If you could rephrase it or re-ask. Yeah, I mean, in this case, yeah, so if all the groups are activating, it's very difficult to only add one chloride. But in our case here, we have an activating group and a deactivating group. And chlorine itself is slightly deactivating. And so for things that are slightly deactivating or deactivating, it's quite simple to add just one, because as you add it, the ring gets less reactive. And because it gets less reactive, you can stop it easier, right? The rate of the second one is slower than the rate of the first one. And that's what makes it for a very easy way to control single versus double addition. In this case, we have a moderately active or, free electron neutral ring with one electron donating group and one electron withdrawing group. And so the monochlorination is pretty easy to control. Okay, any more questions? We have just one electron withdrawing group on meta to leaving group. Is that enough to do SNAR? It would be a tricky substrate for SNAR. It might work, but I would think it would be a tricky substrate. It's certainly less likely to work than the case that we have in this problem where we have two electron withdrawing groups, ortho and para. It's very ready to go. Just one electron withdrawing group meta, it's medium. Yeah, someone's asking in the lab if we wanted more chlorination, we could just let it run longer. Probably. It could also be possible that as you chlorinate, it becomes more deactivated, and so the reaction becomes more challenging as it goes longer. So you need to maybe crank up the temperature or something. But it should be something within our control as the chemist. And yeah, I'm sorry. Wait. Wow, I'm crazy. Someone just said, isn't one only ortho/para to the ketone? Absolutely correct. I'm being crazy. Yeah. The methoxy group is only ortho to the ketone. But it still is ortho to an electron withdrawing group, which is why it's accelerated toward SNAR. But of course, these are meta, and I made a mistake earlier. One. Yeah, that's a mistake. I was in a bit of a dash to make this PowerPoint, so I do apologize for the couple of mistakes here. But yeah, any more questions? Okay, so assign the oxidation level. I'm going to give you like 3 minutes to do this. This should come pretty rapidly, and it is something that's quite easy to practice. Yeah. So 3 minutes. Interesting. Okay, let's talk about these. We can go through them together. You can just post your answers in the chat. What did people get for this first one? Yeah, so I'm seeing a lot of 4s. So I saw 1, and we're going to count the double bonds in the aromatic ring as oxidation levels. So you have 1, 2, 3, 4. So it should be 4. Okay. What about for the second one? It's also 4. And so we can count that the same way. 1, 2, 3. And we know that triple bonds each count as 1. So 4. 1, 2, 3, 4. This is, of course, benzene, which we learned about in this morning's lecture. What about this next one? 3, lots of 3s, great. We'll do this one here. And sorry, let me be clear. 1, 2, 3. Okay, someone said 6. Yeah, so we're gonna count 7 here. So 1, 2, 3, 4, 5, 6, 7. And so we have to count the 2 carbon-nitrogen bonds here. It's gonna be 7. Okay, what about this compound here? Yeah, so we got a lot of 4s, good. 1, 2, 3, 4. And the last one, tricky because it's also 4. Good. I think that this is something that we should all be able to do at this point. Practice it. It's very easy to practice. Should be free points on any sort of exam, right? So don't make mistakes here. Make sure that you really understand the way this works. The easy mnemonic that we can remember is that loss or gain of water is the same oxidation state. So this is oxidation level 1. But if we lose water, it makes an alkene, which is also oxidation state 1. We have an aldehyde or a ketone, and we add water to make it a hydrate. This is 2 and also 2. Yeah, so a couple people are asking about the oxidation level of non-cyclic ethers. Kind of wondering that in lab lecture. You mean for something like this? This is kind of the point where oxidation level is best recognized as something that's just semantic. It's a useful way for us to categorize these molecules when we think about oxidation and reduction reactions. But the question here is this oxidation level 2 or oxidation level 1? If you consider the whole molecule, certainly oxidation level 2. If you consider this part of the molecule, it's only oxidation level 1. We wouldn't ask a question like that. I think I'll make sure we don't. It's ultimately just a semantic difference. Yeah, not really particularly useful. Any more questions? Yeah, so someone asked if an oxidation level of 0 covered both a cycloalkane and an unsaturated alkane. So are both of these zeros? For oxidation level, yes, they're both 0. This is different than degrees of unsaturation. But for oxidation levels, they're both 0. And someone says in lecture, Felix mentioned that methylpropionate, which is the methyl ester, is oxidation level of 3. You would, of course, then be counting it like this. Once again, this is mostly semantic. The difference between cyclic and acyclic ethers is mostly semantic. We wouldn't ask a question like that in an exam. Any more questions? Okay. Problem 5. Since we're running out of time here, I'm just gonna start going through these problems. And so we'll extend a bit past 9, but unfortunately can't give you the full time it would take for you to work out this problem on your own. If you want to work on these on your own, I will be posting a recording so you can watch it later if you'd like. But when we look at this molecule and see these very strongly basic conditions as well as the reaction outcome here, we want to start thinking about chemistry that we learned in class just this morning. And so these sodium amide ammonia conditions are quite classic conditions for the formation of benzene from aryl chlorides or aryl halides. And so when I see these, I'm keyed in right away to a benzene problem. And so we learned, we just talked about benzene. And so in these reactions, there are elimination addition reactions. The first step is the elimination of the aryl chloride by our very strongly basic reagent. And so in this case, our sodium amide, very basic, will protonate aromatic ring to do an elimination of the aryl chloride. This generates our benzene intermediate, shown here. Now, in class, we talked about how benzenes, in most cases, are fairly unselective for the following nucleophilic addition, right? The next step will be the addition of our nucleophile to the alkyne or the benzene. Now, in most cases, there is also the competitive pathway, which is the addition to this terminus of the alkyne. But in the case of this molecule, you have this hindering group here that will sterically encumber any approaching nucleophile. And so in that way, we can get selectivity in this benzene reaction for this less hindered trajectory. And so while benzene reactions can be unselective, they can also be selective based on molecular context. And so in this molecule where we have an unsymmetric benzene, we do see selective formation of, and I just shifted the double bonds around in here, it doesn't really matter. And so this can protonate on ammonia to give us our product. Okay, so this is also yeah. So this is an application of the benzene reaction of SNAR reactions using unsymmetrical aryl chlorides. And so, yeah, there's a question in the chat about where the benzene will form, but it can only form in one position here because we have the aryl chloride only has one adjacent hydrogen. And so I mean, that is a good point, is that a way we can also gain selectivity in these benzene reactions is to have only one hydrogen available to be removed. Any other questions on this? Okay, let's move on to problem 6. This was my less fun way of drawing it, way more fun to use PowerPoint. Okay, so this next reaction is the PCC oxidation of an alcohol. So PCC is pyridinium chlorochromate. So it looks like this. And it has a pyridinium counter ion. This is quite electrophilic at chromium, and so our nucleophilic alcohol attacks. We form the following intermediate. I'm going to abbreviate the terpene group as R. Okay, so it makes an intermediate like this. This can now collapse to eject our leaving group. We're also going to be doing a proton exchange here. So the proton from this oxygen will move to this oxygen. It's going to happen in an intermolecular fashion by protonating various solvents and exchanging those protons. So ejection of the chloride plus a proton transfer event, which I will abbreviate PT, gets us to an intermediate that looks like this. Okay, and now that we have an intermediate like this, base in our reaction mixture, be it the chloride minus, can now come down and subtract this hydrogen, which ejects our activated chromate ester to give us the aldehyde product. In general, this follows a very common scheme for us when we think about oxidation chemistry, where most oxidation reactions occur as follows, right? Where we activate our alcohol toward oxidation through some activated complex. In this case, this is our pyridinium complex, pyridinium chromate complex. In the case of the Swern oxidation, it's different. And so depending on what the oxidation is, this X group changes identity. And so you should be aware of the different ways we can make these activated complexes. And then elimination of that activated complex can allow us to form our desired oxidized product. Okay, and so I saw a question in the chat, which is, when the alcohol attacks, why doesn't it just kick out the chloride? The answer for that is that I don't know the best way to say this, but is that we just observe that it doesn't. So this is like, it's like an E1CV type process wherein an attack occurs, it forms a well-defined intermediate, similar to how in all our other reactions, or in many reactions, we also form a tetrahedral intermediate. So we form a tetrahedral intermediate of some sort. In this case, it's not tetrahedral, it's 1, 2, 3, 4, 5. It's like bipyramidal. But this is a defined intermediate, then is ejected the chloride. Does the elimination not occur through an intramolecular mechanism? So for PCC oxidations, yeah, that's a good point. You can also invoke an intramolecular mechanism. I have seen both in the literature. So you could invoke a mechanism that looks like this as well. Yeah, I've seen both. Maybe in class we did this, so this is better, but I've seen both. Could a proton transfer happen before the chlorine leaves? I think that's probably, that's possible. I don't know if there's a good rationale for either. Any more questions? Okay, if there's no more questions, this is all I have for you tonight. Join me again tomorrow. We'll do another bit of review. And tomorrow we're gonna have a dedicated amount of time just for questions that you have from the lecture so far. So next week, bring any questions you have with lecture material from either the problem sets or previous midterms. We'll try and tackle all of those. And so we'll have some time allotted for that, as well as another worksheet. And so hopefully we'll all feel really good going into the exam on Thursday. But I guess I will see you then. Have a good night, everybody.